Honda 4WS, a steer angle dependent four-wheel steering system. The Honda 4WS system, which is based on a simple and reliable mechanical design, is to be featured in the new Honda Prelude. This original Honda 4WS system is the first in the world because the rear wheels are steered in either the same or opposite direction as the front wheels. A wide range of Honda technological know-how has been put to use in the setting of front and rear steering angles. When the steering wheel angle is small, same direction steering is utilized. This provides ease in handling at high speeds. The system changes to opposite direction steering when a large steering wheel angle is needed for increased maneuverability at low speeds. Technological development of suspension and tire design has advanced to the extent that handling of automobiles has reached a stage of maturity. However, handling and maneuverability are dependent not only on the front wheels, but on the rear wheels as well. As all four wheels work together effectively, the Honda 4WS system has brought vehicle steering to a higher level of handling performance. At low speeds, this system reduces the minimum turning radius and reduces the difference in turning radius of the front and rear wheels. At mid to high speeds, lane changes can be made smoothly at the driver's will and in turn creates a feeling of stability. Now let's take a closer look at how the Honda 4WS system affects vehicle handling and maneuverability. Before we actually examine the 4WS effect, it is important to understand what sort of forces are at work when a car is in motion. Automobile motion is produced entirely by friction between the vehicle's tires and the road surface. This friction is known as grip. When the vehicle is traveling straight and then enters a turn, a variance between the chassis' direction of travel and the tire angle is generated. This is known as a slip angle. Through this slip angle, lateral friction on the tread surfaces which make contact with the road surface is developed according to the tire angle. Among the forces brought about by this friction is cornering force, which is the chassis vertical force that causes the vehicle to turn. The cornering force, which is generated at the front wheels, has an effect on the vehicle's center of gravity, causing the vehicle to rotate around the center of gravity. This movement is known as yawing. Grip. Slip angle. Cornering force. Yawing. Now that we fully understand the meaning of these terms, let's take a look at the differences between turning with the conventional two-wheel steering and the new Honda 4WS system. Initially, let's take a look at high-speed turns. As an example, let's start with lane changes. First, lane changes using conventional 2WS. And then 4WS. Now we'll raise the speed. When viewed in slow motion, it's easy to see the large amount of rear-end sway. And now 4WS. Notice the improved stability in changing lanes. But what causes this difference? Let's take time to analyze steering using both systems. First, the two-wheel steering system. As the driver begins to change lanes, he turns the steering wheel. A slip angle is developed in the front wheels, and cornering force is generated. This creates yawing around the vehicle's center of gravity. After this, a slip angle develops in the rear wheels, and cornering force is generated in the back of the vehicle as well. Finally, the direction of movement changes. The vehicle moves into the next lane, and the driver turns the wheel in the opposite direction to continue moving straight. With this, cornering force is again generated in the front wheels, and yawing is again developed. The time needed for opposite direction cornering force to develop in the rear wheels causes a high degree of yawing in accordance with the inertia of the vehicle. This results in sway in the rear end of the car. The driver then compensates for this yawing by operating the steering wheel until a stable, straight direction is obtained. This is how the steering function operates under these conditions. With a 2WS system, these effects occur during lane changes. Now let's take a look at lane changes with the 4WS system. When the steering wheel is turned, cornering force is generated simultaneously at the front and rear wheels. And the vehicle changes lanes with little yawing. After the lane change, the steering wheel is turned in the opposite direction. The cornering force corresponding to the front wheels is immediately generated at the rear wheels, again lessening the yawing effect. Excellent handling results. With only a small amount of steering wheel operation, the vehicle can be returned smoothly to a straight direction. With 4WS vehicles, the difference between chassis direction and actual motion direction is quite small, and yawing is held to a minimum. For minimized steering wheel operation, and increased stability during lane changes. The difference between the 2WS and the 4WS is easy to see with this superimposed scene. The front shows the 2WS car, while the back is the 4WS car. The delay in turning motion is also minimized when cornering, decreasing the need for driver prediction of handling reaction. And handling is improved even when driving in a straight line at high speed. In addition, simple, stable steering corrections can be made when the vehicle is subjected to crosswinds, rough road surfaces, or other external disturbances. The new Prelude takes tire grip strength to its limits through the use of a four-wheel double wishbone suspension system. The 4WS system makes the most of this grip strength for superior handling and maneuverability with less driver effort at mid and high speeds. Next, let's take a look at the effect that 4WS has when making sharp turns at low speeds. First, let's analyze the differences between the 2WS system and the 4WS when making a U-turn at low speeds. As can be seen, the 4WS turns with an extremely small turning radius. This can easily be shown by the difference in the center of turn. With the 4WS system, the front and rear wheels turn in the opposite directions, bringing the center of turn to a much closer position. Next, let's compare the tracks of the front and rear tires when turning a corner. Note that the front wheels pass over the same paths, while the rear wheels travel in entirely different paths. The 4WS system also performs extremely well when making tight turns on narrow roads where a very small turn radius is necessary. And the 4WS system makes it easy to back into tight spaces, such as a garage. In this case, the movement of the rear wheels is extremely important. Parallel parking is easy too, even in tight spaces such as this. When the steering wheel is turned, fully pulling out of this type of space, the rear end of the 4WS vehicle moves more than a 2WS vehicle, so caution must be exercised. We just had a look at how the same direction and opposite direction 4WS affects handling and maneuverability. Generally speaking, a long wheel-based vehicle provides a more stabilized ride. While a tighter turning radius is provided with short wheel-based vehicles. With 4WS vehicles, the center of turn is far when the same direction steering is affected, providing a handling feel which is similar to that of long wheel-based vehicles. Conversely, a fuller rotation of the steering wheel produces opposite direction steering, and the center of turn is made closer, providing the feel of a short wheelbase vehicle. Let's take a look at this relationship on a graph showing handling characteristics. The horizontal line represents the steering wheel angle, while the vertical line shows the amount of steering wheel operation necessary to move the front and rear tires of a vehicle 1 degree. With the 4WS system, the change in tire angle is small in comparison with the degree of steering wheel operation when the steering wheel angle is small in the mid to high speed range. This allows moderate slow operation. At slow speeds where a large steering angle is required, on the other hand, a slight amount of steering wheel operation causes a sharp change in the tire angle. This provides quick, crisp handling and maneuverability. In these ways, the 4WS steering system provides a variety of improved handling characteristics, from slow, subtle steering to quick, sharp turns. The Honda 4WS system has realized these variable handling characteristics through positive control of all 4 wheels, providing both safe performance and sharp handling. These represent the main characteristics of the Honda 4WS system. At this point, let's explore the construction of the 4WS system. The Honda 4WS system is comprised of 2 systems, a front gearbox and a rear gearbox. These are connected mechanically by a center steering shaft. We'll use this working model of the 4WS mechanism to take a look at system operation. When the driver turns the steering wheel, the rack and pinion in the front steering gearbox moves the rack in the axial direction. The stroke of this rack steers the front wheels and simultaneously rotates an output pinion shaft through another rack and pinion in the gearbox. The output shaft transmits the turning angle of the steering wheel through the center shaft to the rear gearbox. The stroke rod moves in an axial direction in accordance with the turning angle, and the rear wheels are turned by the tie rods. At approximately 120 degrees, same direction steering reaches its peak, while a neutral position is reached at approximately 240 degrees. If the steering angle exceeds this level, opposite direction steering gradually takes effect. Now let's take a look at the construction of the rear steering gearbox and how it operates. The rear steering gearbox houses a variable gear ratio mechanism which reverses its output direction depending on the steering angle. Various parts are found in the system structure, including the rear steering gearbox, an eccentric shaft, an internal gear, a planetary gear which contains an eccentric shaft, a slider, a slider guide, and a stroke rod. These parts make up the rear steering gearbox. Now let's take a closer look at how the rear steering gearbox actually operates. The front steering angle input from the center shaft first rotates the eccentric shaft, after which an internal gear fixed to the case engages with the planetary gear, which rotates and orbits within the fixed internal gear. This motion is transformed into a lateral motion by the slider. Let's make a further analysis by looking closely at the movement of the eccentric shaft of the planetary gear. The track of the center is shown here, from the same direction to an opposite direction when the steering wheel is turned to the left. And it moves as shown here when turned to the right. This is the result when the wheel is turned back and forth in repetition. When the slider is connected, the vertical movement is absorbed and left and right movement is output to the stroke rod for either same direction or opposite direction steering. Here we can see that when the steering angle is at approximately 120 degrees, same direction steering is at its peak, while a steering angle of approximately 240 degrees brings about neutral steering, and any larger angle causes opposite direction steering. Now let's take a look at the relationship between the steering wheel angle and the front and rear wheel steering angles. When the steering wheel is turned from the neutral position, the front wheels respond as shown by the blue line. In relation, the rear wheel steering angle changes smoothly according to the operation of the variable gear ratio mechanism in the rear gearbox. The maximum rear wheel steering angle is approximately 1.5 degrees in the same direction steering mode and approximately 5.2 degrees when in the opposite direction steering mode. These angles are set so that all drivers, even beginners, feel completely comfortable. The angles also allow optimum utilization of the characteristic advantages of the 4WS system. This mechanical 4WS system is extremely responsive and highly reliable. In order to improve the system's reliability, pulley load has been applied for both the front and rear gearbox assemblies, preventing backlash. Also, the rear gearbox assembly is designed so that it cannot be taken apart. It features high-precision components and, naturally, is subject to stringent inspection during assembly, assuring reliability. The Honda 4WS system distributes the stress of cornering and bad road conditions to all four wheels, decreasing steering wheel kickback. In addition, it provides sharp response and gentle handling characteristics. Next, let's take a look at how to adjust the Honda 4WS system. We'll explore the procedures involved in making an off-car check of the rear gearbox, as well as in making the backlash adjustment when assembling the front gearbox. First, make an off-car check of the rear gearbox. Before removing the rear gearbox, always be sure to check the wheel alignment and check that the steering wheel is in the center position. Also check the turn angles of the tires. The directions of the rear gearbox shaft and gear backlash appear as the right and left side rigidity of the stroke rod. Because of this, we'll explain how to make the right and left side rigidity check, as well as how to measure starting torque when the stroke rod is moved to the right and left. First, check rigidity to the right and left. When removing the rear gearbox from the vehicle, use this center lock pin to fix the steering wheel in a neutral position. When the gearbox is removed with the center lock pin in this position, it is recommended to hold the gearbox in a vise using aluminum plates. Remove the center lock pin. Remove the dust seal. This procedure requires the use of some special tools. Attach stroke rod holders A and B to the tie rod stopper. Then tighten stroke rod holder B. This holds the stroke rod in place. Prepare a steel plate like this for use in attaching the gauge. Use a torque spit to attach the plate to the gearbox case with the cap bolt. Now fix the inspection gauge into place. Set the dial gauge on the steel plate so that the cutout section comes in contact with the tip of the dial gauge. Next, attach a torque wrench. Apply the specified load using the torque wrench and check the movement of the dial gauge. Check to see if the value is within the standard range. This operation is used to measure left and right rigidity. Next, we'll see how to measure starting torque. First, remove all tools except the inspection gauge. Now attach a torque wrench to the inspection gauge. Turn the wrench a number of times and read the starting torque within a 45-degree range to the left and right. Check that this value is within the standard range. These two procedures constitute the rear gearbox off-car inspection. Next, we'll explain how to inset the driven pinion holder and the adjustment of rack and pinion backlash, which are performed by disassembling the front gearbox. First, let's talk about the actual assembly procedure. Place the rack in the neutral position by adjusting it to a position which is 63 millimeters from the rack bush retainer. Notice that the pinion gear is set at an angle. The housing and shaft alignment marks are aligned by shifting and pressing in on the shaft. Next, attach a driven holder washer with the right-hand mark showing for vehicles with right-hand steering. The inscribed line is aligned with the shaft. Note that the washer should be placed with the left-hand mark showing for vehicles with left-hand steering. Next, tighten the driven holder bolt to the extent that the driven pinion holder assembly may still be rotated. Turn the holder all the way to the left, putting it in a free position. Next, remove the cap bolt. Now attach the rack adjust gauge holder. Replace the tip of the dial gauge with the spindle gauge attachment. Set the dial gauge in the holder and lock it down. The spindle gauge attachment should be in this position. Now set the dial to 0. Turn the driven pinion holder to the right and make the backlash adjustment so that the standard value is attained. This holder is eccentric, so backlash can be adjusted by rotating it. Note that the driven pinion holder must be rotated to the left for vehicles with left-hand steering. Now tighten the holder bolt with the prescribed torque. Once the backlash adjustment is complete, remove the dial gauge. And attach the cap bolt. Attach the dust cover and fix it in place so that the band is in the proper position. This completes the insertion and adjustment procedures for the driven pinion holder. After reassembling the gearbox, check that the steering wheel is in the neutral position and check and adjust wheel alignment. Finally, be sure to check side slip as well as tire turn angle. The Honda 4WS system, a steering system that utilizes all 4 wheels of the vehicle to provide unmatched handling and stability.